Hey everybody, thanks for coming to Skookum. My name's Hunter Loftis, and I'm the director of technology here, and I live most of my life, in code somewhere programming, and I wanted to make some sort of a presentation that's accessible to people who aren't quite as nerdy as I am, and that's what this is about. It is going to have a little bit of technical stuff for those of you who are nerds like me, but a lot of this is going to be focused on sort of the business aspects of building things in software, right? So. I'm curious, who here works with programmers but doesn't program? Just so I have an idea. Okay, excellent. So awesome. I'm trying to embrace the business side of things today. I tried to dress like one of you, but I've already been told that it's too wrinkled. I'm supposed to iron these things. So I'm already failing, but hopefully the talk is a little better than the presentation. So computer science for regular folks. I lied about the slides. I said there are going to be 0 slides. The slides are purely for me, right? These are just my notes. So there's going to be very few slides, so don't worry about those. And everything that I'm going to talk about here is going to be available online, and all of the demos are going to be available at Skookum's GitHub repository. So the thing that prompted me wanting to talk to business people is that I find a lot of our sales guys, a lot of our project managers, and a lot of our clients are frequently asking me for a level of effort, right? And I find that people are surprised when things that sound trivial, that sound like a trivial feature, take weeks or thousands of dollars to develop. And also a lot of our clients are frequently surprised when something that they think is going to be really hard, we write 3 lines of code or flip a switch in a config file somewhere, and then boom, it's done, right? So I think that the disconnect comes from people who don't code not really understanding the kind of thought process you go through when you code, and not really understanding what programming is. And obviously this isn't going to encompass everything that programming is, and some of you coders might get a little bit upset with me because there's some half-truths in here. But I'm going to try to explain what I feel like when I'm coding, and the kind of thought process I go through and that my team works through, so that maybe some of the business guys will leave here with a better understanding of what exactly is happening when you put in a feature request, and then your developers make some sort of a crazy estimate about it, what might lead to that kind of an estimate. So feel free to interrupt with any kind of questions you have. I'd like it to be kind of conversant. I'm also gonna hope that you guys will participate with me a little bit, because I need a few volunteers at various points in this. We're not going to deal with any code, but we are going to build a working piece of software through this presentation. So how does a developer see a computer? This is the first thing. You start a new project and you're looking at the computer. It doesn't do anything that you need it to do yet. So so how do you interface with that as a programmer? And myself, I look at a computer as like a newborn that can do math, basically. And you've got to bridge these 2 divides. You've got this newborn. It's like a blank slate that you need to teach something about the world. And the slate can already do basic mathematical operations, but that's about it. And there's this whole other concept of the universe over here that you're going to have to convey to this thing. And so what you end up doing is basically philosophy. I tell people that computer science is like a philosophy degree with job prospects, because all we ever do is we sit around talking about ideas and how you would define a concept. We talk to each other about what's the purest or the most truthful way of defining some kind of a concept. And once you define a concept to a computer, that new concept is a building block for more complex, more abstract concepts. So you start out with a couple blocks that the computer gives you, and you use those blocks to build more blocks and more blocks and more blocks, and eventually you come up with this really abstract idea, and you've defined a whole universe. And once you define that universe, you have all these actors and you have all these set pieces for it. You can use the universe kind of like Jim describes it as a choose your own adventure story, right? You have all these actors now that you've defined their behavior and what they are and how they work. And you can now write a story with them. And the story needs to be coherent from start to finish, but it also needs to be dynamic, because you're not reading the story, the user is reading the story. And he's choosing his own adventure. He's figuring out what he does. So at every point, all of your actors and set pieces need to do something that makes sense within the context of this story. So that's how I look at a piece of software when I'm about to start developing it. And I think that makes more sense if you actually go through the process. So what we're going to do today is we're going to build a whole working piece of software in the next 45 minutes, right? And this software is going to be based on an old school challenge. Is anybody here from my generation familiar with Doom and Wolfenstein and these types of old 3D games? Raise your hand if you've ever played. Okay, awesome, good. Well, these are the games that inspired me to start programming. When I was a teenager, I really wanted to make video games. And some of the challenges that these guys face were just mind-blowing, right? Like Wolfenstein in particular, it had to run on 40 megahertz processors, right, which is approximately 65 times slower than an iPhone 5. It had to run with 2 megabytes of working memory, which is approximately 512 times smaller than an iPhone's working memory, right? So take an iPhone and divide it by like several hundred orders of magnitude, and that's what these guys had to work with. And I think a lot of the tricks and clever things they came up with are still pertinent today, because as web developers, we deal with a wide range of devices, a wide range of platforms. With some have a lot of memory and some don't. And so some of the clever ideas that these guys had to overcome, 20 years ago, are still things we can learn from today. So Wolfenstein was written in 1991. It was written by a team of 6 artists and developers, and it took them 6 months to build. And because of the building blocks that we have now as web developers, one guy can build the same thing in a couple of days, right? Which I think is just an astounding leap forward. So, so that's what we're going to do. We're going to build a Wolfenstein engine right now. Any questions before I go on? Does everybody know what a Wolfenstein engine is? It's kind of like a 3D shooter game. So you're like running around. There's walls. There's other players. You've got a weapon, right? So that's what we're doing. So we're going to start with a couple of basic building blocks. And this is where I'm going to kind of leave off with the slides. I need a volunteer who can see the screen, who's going to be a driver, who's going to be the driver in our shooter game.
Douglas.
What's that?
Douglas would love to.
Yeah? Who's?
Sure.
All right. Fantastic.
Lovely to meet you, Hunter.
Hey, I'm Hunter. You said Douglas?
Yeah.
Okay, cool. You are going to be the driver. So that's a wireless keyboard. It's connected to this computer.
Okay.
Try not to press anything except the arrow keys and A and D. All right?
And those would be in English. Yeah.
Okay. Yes. Yeah. So just you can sit down. You're going to be the driver throughout this whole presentation. So, so I'm going to trust you because you're connected to the same computer I am now. All right. So we're going to start with a blank canvas, right? This is what we're working with. It's just we start with nothing, right? This is an empty universe. We haven't defined anything yet. But we do have a couple of building blocks that the web has given us, just because we're web developers, right? A browser understands the idea of a point, at least a modern browser does. The idea of a point, right? Mathematical x-y coordinate. It understands the idea of a line, which is basically just the space between 2 points, so really a line segment. And it understands the idea of a bitmap. Does anybody not know what a bitmap is? I'd be happy to explain it. Okay. All right, Chad. A bitmap is basically a grid of pixel colors. Any picture that you've ever taken is a bitmap, right? And a browser knows pretty well how to work with bitmaps. It can display a bitmap, but more importantly, it can also display pieces of a bitmap that you specify. So these are the only 3 things that we have to work with. This is it, right? We're going to build all of Wolfenstein starting with these 3 building blocks. And this is what a programmer's doing. He's saying, all right, I've got this goal way over here that I'm trying to build. And I've got these couple of building blocks. And how can I use these to assemble this big system? So the first thing we need to define is the player, right? So somebody tell me, like in a game like Wolfenstein, what is a player? If you can work with a point and lines and a bitmap, can anybody think of what a player might be? It's not obvious, but I think you're going to sort of start to see how this works in a second. So in Wolfenstein, as a player, you have a position in the universe, right? And a position can be defined by a point. As a player, you also have a field of view. You have a leftmost field of view and a rightmost field of view. And everything between it is the thing that you see, right? So we can define a player as a combination of 1 point and 2 lines. Does that make sense to everybody? All right, so I kind of want to, here, I'll use that later. I'll use the prop later. So a player can be defined something like that, 1 point and 2 lines, right? So Douglas, right?
Yep.
Would you walk our player around a little bit? You can spin him with the arrow keys. You can move him forward and backwards. All right, so like right now that's all we've got. We took a point and 2 lines and we made the concept of a player. So now the computer kind of understands what a player is. Does that make sense? Okay. So the next thing we need in the world is some kind of a map. All Wolfenstein levels have a map, and the map is just made up of walls, right? So somebody can tell me, out of points and lines and bitmaps, how you can make a map.
4 lines in a bitmap.
Yeah, a bunch of lines. Yeah, a grid of lines. That's like all of these would work. You could do it with just a bitmap. That's one way. You could do it with a grid system. You could do it with just a bunch of line segments. And we're going to use a bunch of line segments because that's just easy, right? So the map is just going to be a set of lines. So I'm going to turn those on now. So like now we've got a map, right? And Douglas can walk around in this map. And so now the player, like, it has a world, right? It's not a world that really looks like the video games that I'm talking about. But the computer is starting to understand the idea of a map and the idea of a player, right? Does this make sense to everybody? All right, cool. So as you can see, Douglas can kind of walk through all the walls right now. You know, he can wander around, and like, while the computer understands the idea of a player and it understands the idea of a map, it doesn't really know how the two should interact with each other. And to get how the two should interact with each other, you've got to explain to the computer the idea of an intersection, right? Because you shouldn't be able to walk through a wall. It should be able to see that there's an intersection between you and the wall. Does that make sense? So basic math here, what's an intersection? What 2 bits of data do you need in order to make an intersection? 2 lines, yes. And if you have 2 lines and you compute the intersection, what does that give you? It gives you a point. Yes. So now we know that an intersection is just 2 lines and 1 point, and we can enable intersections. So now walk around and you can see that the computer starts to understand an intersection. You can't walk through a wall anymore, and it sees where your field of view is running into walls, right? So that makes sense. Awesome. So now that we've got this intersection here, the computer understands the map and the player, and also now a little bit about how they interact with each other. But we're still not really rendering things in the way, like in a 3D shooter sort of a way. This is still like a top-down map. This would not be a very fun game to play, right? So the next thing we need to do is we need to describe to the computer like about a field of view. So can I get, let's see, I'm going to need 9 people, which is a lot of people, right? Actually, I could probably do this with, let's see, we do this with 5 people. Let me get 5 people who just come up here for a second. Come on, 5 people. There we go. We got 1, 2, 3, 4, 1 more. 5. All right. All right. So you're going to be our main player, right? You're our main player, and then we're going to give each one of your assistants 2 lines, right? So you're going to get 2 lines. Yeah, try not to get them too tangled. You're going to get 2 lines. And yeah, you're going to get 2 lines, Chuck. And yeah, exactly. If it,
Trouble there.
yeah, well, it should. They're all plasticky. It should be all right. Hopefully. Come on, let's do this.
Too tight.
Yeah. Well, son of a bitch. All right. Well, there's no way I'm going to have time to untangle all this crap. So we're just going to use our imagination with these guys, maybe. Let's see. Oh my God. Should have made the lines shorter. There we go. All right. So now, you're the player. Chuck, you're going to be on his left field of view. You're going to be in his right field of view. And I should have planned for more space here. So you guys are going to have to come together a little bit more, right? Like a 60-degree field of view. Chuck is as far left as you can see with your eyes. And Jason's as far right. Okay, so, and then spread these out a little bit so that they're about even. Yeah. So now, this is the concept that we're actually going to try to teach the computer next. We've got a player. He's a point in space, and we've already defined that he has a left line and a right line. But he needs a way of interacting with the world, right? He needs a way of being able to tell when a wall is in front of him and how far in front of him it is and where he's intersecting with that wall. So instead of just 2 lines, we're gonna make an array of lines that sweep across his whole field of view. And each one of these lines is going to run into a wall. For example, this line would run into this wall here. And that line would run into that wall there. And what's an interesting property about these lines and why they're important is because once you measure this one, it's going to be longer than that one. Or it might be, it's like one of these lines is going to be longer than the other. Those lines that are going to the corner are going to be longer than my line that's going here. Based on the distance of the lines, you can figure out how far away the wall is, which also tells you how big the wall is, right? Because you've got a vanishing perspective. The longer the line, the smaller the wall. And that's going to allow us to project these walls into 3D space. So instead of looking top down like we are right now, we're going to be able to make a 3D projection of these things. So hold on a second, guys, and thank you. So Douglas, let me have you walk around now with those. It's the exact same thing we're doing here. You've got a player, and he's got these lines projecting. As you walk around, each one of the lines, after a certain distance, hits a wall. Right? So that's going to be this idea. It's called ray casting. And it's the fundamental element of Wolfenstein, of Doom, and it's the basic idea behind all of those games. And it's the core of what we're going to use to build our game engine. Because now you can see the computer is starting to understand much higher level concepts than just point and line and bitmap. It's starting to understand how these different concepts can interact with each other. So now that we've established that a field of view is just a player and a map and a series of intersections, we can start to do something with this data. Now the computer understands its environment, and we just need to figure out how to get it to render the environment properly. And thank you, guys. That's all I needed you for right now. Yeah. Any questions so far? Does all make sense? Okay. So we want to turn our lines into actual walls, right? So if I were going to draw a wall on the screen, if I were going to like paint a wall here, what elements that we already have would I use to draw, for example, a rectangle? 4 lines. Yeah, 4 lines. Yeah, or you could define it as 4 points actually. But yeah, so if you have 4 lines, you can define the section of a wall. We already have these intersections, right? And the intersections have a length property. So we can combine the idea of an intersection's length with the idea of 4 lines, and we can make a wall that can get closer and further away from you, right? As it's further, it gets smaller. As it's closer, it gets bigger. So that's what we're going to do. So now, all right, so now we have these walls, right? These sort of ugly walls. Douglas, will you walk around the environment a little bit? Maybe kind of try to go out the door so that we can, actually, let me do this. I'll put you back out the door. There we go. And so now kind of, let me have you back up a little bit. And I want you to look to the right until there's only 2 intersections that you're seeing. Yeah, you're good. That's close. Yeah, oh, yeah. There you go. 3 is good. 2 is good. All right. Does everybody see what's happening here? The computer now understands the idea of a wall and how it relates to a player. We're hitting these 2 different walls. This line is a little bit shorter than that line. So when we draw our rectangles, we make that rectangle a little bit smaller than the other rectangle, right? And if you sweep back to the left, Douglas, you'll see that it holds true as we have more and more intersections, right? Now, this doesn't really look like a game of any sort, and these don't even really look like walls, right? Does anybody have an idea how we might make this look more like an actual 3D scene and less like a bunch of cardboard cutouts?
Use more lines.
Yes. Yes, use more lines and thinner rectangles. So that's exactly what we're going to do. So let's go here. And now you start to have a 3D scene. We're doing the exact same thing that we've been doing this entire time, but as Douglas sort of looks around, you should be able to see that he's in a 3D environment now, right? And it feels like we're starting to make a video game. But we've only defined a couple of concepts here. We started with points and lines and bitmaps. We haven't even used bitmaps yet. And already we have a computer that understands the player and the map and that can draw a 3D scene based on that information, right? Does what's happening make sense to everybody? Pretty clear? All right, cool. So now that we can draw walls, there's just 4 lines and an intersection. Do we have any art students or designers in here who know the term for this type of perspective? Well, it is a vanishing point. There's a type of perspective. Come on, we've got this. It's a linear perspective. Come on, people. So, how about, does anybody know one of the primary artists who reinvented linear perspective, rediscovered it in the Renaissance? Come on, we've got a room full of designers. Somebody knows this. Nobody? Well, it's Da Vinci, all right? It's Da Vinci. You could have guessed, and you would have probably been right. But Da Vinci, during the Renaissance, sort of rediscovered the idea of a linear perspective and used it in a lot of his paintings. And that's what we've implemented here. As I zoom back, you can see that there's some similarities between that and this kind of a wall here, right? And that's all we're doing is we're just recreating linear perspective with math. So now that we've got linear perspective, we're going to build some lights into this scene. All right, Corey, it's time to redeem yourself. That's true. That's true. It's time to redeem yourself. There's another type of perspective that involves what the atmosphere does to colors as they're in the distance. Does anybody know? It's also a big thing with Da Vinci. Nobody knows this shit? All right. It's atmospheric perspective, right? As something gets further in the distance, you see it fade into blue, like a misty sort of a blue, low saturation. We're going to use an exaggerated type of atmospheric perspective to make our scene a little bit more 3D, right? So the way we're going to do that is by computing the distance and using the distance to brighten or darken the wall that we're seeing. So Douglas, would you walk around a little bit now so that we can kind of see that as a wall gets further in the distance, it gets darker. So if you back up, that whole scene will fade. And it's going to give you a much more sort of a deeper sense of the 3D, right? So yeah, so now we have linear perspective and we have atmospheric perspective, all with just those three basic building blocks. So all we're using is the idea of a wall that we have defined, right? This is one of the first places where we're not actually using any of the built-in building blocks, right? We're not using points or lines or bitmaps at this point. We've defined the idea of a wall. We've defined that concept to the computer, and it understands it now. We've defined the idea of a player, and we can combine those two ideas, and we can make a new idea. That's the idea of the light that a wall has when a player is near it, right? And so at this point, we're totally outside of that base layer. We're way up high. We've abstracted this idea, and we're working with our own ideas instead of the built-in ones that the computer gives to us, right? And there's a Da Vinci thing with atmospheric perspective right here. So now, this would not be a very fun game to play, right? Everything is gray. It's not a very interesting scene. So we're going to try to give this thing some textures. We're going to give these walls some texture. So now, could I get one person to hold this for me again? Come on, somebody come up here. Please. Yeah, just hang on to that. Can somebody tell me what we might do with the concepts that we've defined so far in order to cast these rays onto a wall and then paint the part of the wall we have there onto the screen based on the building blocks we've got, which are points, lines, and bitmaps? Any ideas? Somebody has an idea for which one of those we might use to paint the wall. Yes, we'll use a bitmap. Yes, exactly. So what we're going to do is we're going to take the bitmap of a wall, and we're just going to slice out the piece of it that's between these two lines. And as you turn, like if you turn to your left, right, you'll start seeing this part of the wall, and we'll slice that. If you turn to your right, we'll start seeing that part, and we'll slice that part of the bitmap. And slicing the bitmaps and pasting them back together on the screen is going to give us a texture. So we can do that, right? So Douglas, will you kind of walk through this scene a little bit for me? Right, so now we've turned our really, really basic map, which is just that, into something that understands the player, into something that understands his field of view, and projects some walls, projects some high-definition walls, gives them lighting, and then gives them texture. Right? And so from those basic building blocks, we've built an environment that you can recognize now. And you can recognize where you are. And this now makes sense to a human. So we've bridged that gap, from math, the pure language of math, up to something that a human would understand, and a universe, an environment that a human would understand. Right? So as we walk around, you can see that there's a recognizable environment here. So, yeah. So there we go. And So those are textures, right? A bitmap and a wall. So the last thing that we're going to build for this game is the idea of a door, right? So we have all these concepts defined already. We have walls, and we have points, and we have lines, and we have intersections, we have players. Out of these building blocks, can somebody tell me what we might be able to combine to teach a computer about the idea of a door? What is a door really? In its simplest terms. What's that? It's a mobile wall. Yeah, exactly. But more specifically, let's talk about a rotating door. Yes, it is a door. It's a wall that rotates about a point, right? So we can define this concept to the computer with just the building blocks. And once we teach the computer to take the idea of a wall, the idea of a point, and just make the wall rotate around the point, we can have a door. So now, let me go up here. So now we can have these doors that open as we get near them, right? And close when we get far away. That's because we've taught it about a player, so it knows how close the player is to the wall. Taught it about a point, so it knows what to rotate around. We've taught it about a wall and how to draw a wall. Once we have those three ideas together, we can make a door that opens when a player approaches, right? Which is an important part of any video game. And a wall and a point and a player. So when you're talking to your developers and they're trying to explain to you how they're going to do a particular feature, what they're really doing is they're working backwards. They're thinking, in order to implement this feature, I've got to teach the computer about all these different ideas, right? All these different concepts. It has to understand these things. And they're saying, how can I work backwards and meet the computer at where it begins, you know? And how can I decompose these ideas into simpler and simpler and simpler ideas until it finally gets it? So to a human, the idea of a door is a simple idea. It's a simple concept that should be a simple feature. You know, everybody here understands what a door is and how to use one pretty intuitively. But a computer doesn't. And as you can see, it takes several levels of abstraction before you can teach a computer what a door is and how a door works. But once you learn how to do that, you can take some simple ideas, points and lines and bitmaps, and you can expand them into much more complicated, much more humanistic ideas, right? And with that, you can make a game. And this game's available at GitHub from Skookum. It's open source, so you can see how it works. It's pretty simplistic. You can actually play it online, I think. Yeah, and you just use the number keys to set what level of abstraction you want. And one of the interesting things about a game like this, because we now understand how complicated these ideas are, but like how we're just taking the same idea and repeating it across the screen, you can actually make this game look very different by just changing a couple of things. Like this is an example of where somebody who's not a programmer might think this is really, really complicated. It might take weeks to do, whereas a programmer would recognize that it's literally the change of one variable. And the example that I'm going to use is the resolution of this game, right? Let's say your client came to you and said, I want to run this game on iPads. It needs to be much, much faster and simpler. It needs to work on a smaller screen. So we want to have it run at a much lower resolution. Well, we can do that. Which is a simple toggle switch, right? Just like all we're doing here is drawing a couple of walls instead of a lot of walls. We're just spreading out our field of view. Or if you came in and you said, hey, this game looks like shit. We want it to look really, really good. We want it to be able to compete with the contemporary games of 1991. You can change the same switch. And you can have a very high resolution thing where you can actually recognize that that's Melissa. And you can recognize that that's the Charlotte skyline and you know, that this is our refrigerator and stuff. You can almost read our little plaque. And that's a simple thing. That was an easy thing just because it's a concept that the computer already understood. So we didn't have to invent anything. We just had to change a couple of numbers, you know. And that is Skookumstein 3D. Does anybody have any questions? Yeah.
So whenever you're walking around Melissa actually like a 2D plane?
That's a great question. So one of the things I didn't talk about was how you make characters and NPCs, and there's all sorts of other stuff that Wolfenstein does. But yeah, Chad, you're right on the money. Melissa is actually not like a whole 3D person. I mean, no insult. but she's just a wall. She's like a cardboard cutout. No personality. And so yeah, as you walk around her, you can actually see if we get really close to her, she'll turn to face us again, right? So she's just kind of like spying on you from wherever you are. I've trapped myself in her desk somehow. There we go. And yeah, so exactly right, Chad. Melissa's just a wall there, and it's a wall that understands the player and knows how to turn, to rotate, to always face the player. Yeah, good question. Any other questions? Any other thoughts? Yeah? Sorry, who asked? The textures are a very high-tech thing. I walked around the office, I took photos of the walls with my phone, and those are the textures. So yeah, so I'm sure one of our designers could have done a much better job, but it works. It's recognizable. Yeah, any other questions? Anything that you see here that you're wondering how it happened? There is something in here that I haven't explained.
Change the lighting top and bottom.
Can you change the light? Yeah. Yeah, we did change the lighting. And this is how. I'll go to a place that has no wall. It's just a background image. And this is what they did too, actually, in Wolfenstein. Once it has all the walls around it, it gives the illusion of like being a floor and a ceiling. But it's really just a gradient in the background, right? It's just smoke and mirrors. Yeah?
How do you do the ceiling?
How do you do the ceiling? You mean the ceiling light?
Yes.
Because, yeah, the ceiling is just that gradient, but how do you, for example, like put that up there? That is also just a wall. Everything in this simulation is a wall, right? And yeah, even the refrigerator is a wall, which is actually why there's, actually, let me ask this. Does anybody know why I omitted putting the couch there or the table here? Anybody make a guess?
It's not the full height.
Yeah, it's not the full height. And we haven't taught the computer about the idea of anything but a wall, right? The computer understands how to draw a wall, but it doesn't understand how to draw a table or even a floor. So this is a great example of where a project manager might be very confused and think that I'm totally lying to them when I've already taught a computer how to draw a wall. And he asks, well, I want to draw a floor now. A floor is exactly the same thing as a wall, just turned 90 degrees, right? It would actually be an enormous amount of work to put floors into this game because we've worked all this time just to define all these abstract concepts in order to teach it what a wall works like. To teach it what a floor looks like would be really hard. We'd have to do basically all this effort again, right? It would be twice as hard as all the rest of the game together. But it doesn't sound like it should be. It sounds like it should be very simple. But yeah, that's why there are no tables or couches or anything that's not a wall here, because that would be an enormous amount of work. Yeah. Anything else? Yeah. Yeah.
What about moving the player in space, like jumping?
Jumping.
Yeah.
There are several ways you could do jumping. So, do you have any ideas, first of all, how you might make them jump?
Yeah, move the walls down and back up again.
Okay, yeah, so a really rudimentary jump, you could just move the whole scene up and down, right? That wouldn't really look very realistic. It wouldn't look very 3D, but it would give sort of the illusion of jumping. But we know more about the walls than we did at the beginning. Like, the computer understands your distance to a wall. So based on your distance to the wall, is there a way that we can make jumping look more realistic?
Move them up or down the percentage amount.
Exactly. And so would a closer wall move, let's see, closer wall would move more, right? Yeah. So you could do exactly that, except instead of just moving the whole scene, when you're drawing a close wall, you really move it quite a bit, and a distant wall just moves a little bit, and that would give you this illusion of a 3D jump. Yeah. These are exactly the sort of things that a software developer has to try to think about. Like, how can we take these concepts we've already instructed the computer about and use them to build new ideas, like the idea of jumping, right? It's kind of hard to describe. Yeah, describe to the computer an idea of jumping. And you could. That's the thing. If you wanted it to be perfect, you could teach the computer exactly what a jump is. You could be very accurate. You could philosophically explain that there's now a z coordinate as well as an x and a y. You could teach it how to use that z coordinate. That would be an amazing amount of work, right? And your project manager probably wouldn't like you doing that because it's pointless. If you can make the illusion of jumping without teaching it about 3D, then you should, probably.
How do you teach a computer that Nazis are evil?
Yeah, that comes with the browser. That's one of the building blocks, like Jim said. Well, you know, that's actually an interesting question because a computer's not even going to understand that idea, really, you know? All you can get a computer to really do regarding the evilness of Nazis or imps is to act like a Nazi is evil, right? So you'd have to define behaviors that make a computer pretend that it thinks that a Nazi is evil, but it doesn't really care. Computer will never care about that. So, yeah.
So, how big of a leap is it from like a first-person shooter to like a 3D, a third person, like in an environment watching them? Like the difference between this and then like when the N64 came out and Mario was, you could actually see Mario.
Yes, that's an enormous leap. It's a huge leap, and the reason for that leap is because if you think about what we've taught the computer about here, oh yeah, this is the one that's live. It's got a different map. So if you think about what we've taught the computer about here, everything we've taught it is in 2D space. So it makes an illusion of 3D, and it has some idea of depth and distance, right? But it doesn't actually know how tall these walls are, right? And it doesn't have any idea of something that's not a 90-degree wall to the player. None of those concepts have been taught, right? We taught it a very rudimentary wall. It's based on the idea of a line. So if you want to teach it about something that's not a wall based on a line, you're going to have to teach a lot more concepts. You're going to have to take that line and make it a 3D line in 3D space. And then you're going to have to teach it the idea of a triangle that's in 3D space. And you're going to have to then teach it the idea of something called a mesh, which is a whole bunch of triangles that are all connected to each other in 3D space. And it's just, it's a big jump, though. Because with this one, these are the only things it understands. So if you can't describe the concept with these building blocks, then you can't do it. So in order to go to 3D, you would have to, this list would get much, much, much longer. You know, 3D line, triangle, mesh, culling, surfaces. You'd have to describe, for example, how light reflects off of things. You know, because as something moves in 3D space, there's a light source, and that light bounces off of the thing and intersects with you.
That's why all 3D games run on somebody else's engine now. So everybody says we're using the Unreal Engine, we're using the Quake engine. They don't build their engine because it takes too much work to do it in 3D to teach it all this stuff.
Yeah.
They let somebody else build this part of the engine, and then they just build maps and the characters.
Yeah, and that's exactly, and they're using the idea of abstracted building blocks, right? They're taking an engine where somebody's already built all these concepts for them, and they're starting with that. You're standing on the shoulders of giants. Then you're building these new game ideas on top of it, right? So whether you're making Grand Theft Auto and teaching the idea of like cars and robbery and battery, or whether you're building, I don't know, Mario, and you're teaching the idea of turtles and, I don't know, pipes and mushrooms, exactly. Yeah. They're both building on similar concepts, but going in very divergent directions. So, yeah. Yeah. Any other questions? These are good questions.
And so this is not, you're not leveraging WebGL or anything like this. Is this all just like transforms on CSS?
This is 100% done with Canvas. So all of this is being rendered with Canvas, which is the closest thing I could do to how Wolfenstein is really built, because they don't have WebGL, So Wolfenstein was really using just a 2D canvas that you're pasting bitmaps on, and that's exactly how this is running too. Yeah. Yeah. Anything else? Cool. Well, thanks, guys. I really appreciate everybody coming, and I'd be happy to talk about this later. Yeah.